Okay, so welcome to my talk, and thank you very much for the invitation to come here. So the topic of my talk will be quantum communication, with focus on quantum key distribution. So basically, what I'm going to show today during my talk is that it's possible to increase or to extend the length or the distance for secure communication using squeezed state of light. So this is basically the bottom line of my talk. Okay, so quantum communication. So what is this? So this is basically a transmission of quantum states over some optical links. And these optical links can, of course, be of different kinds. I mean, it can be standard optical fibers. It can also be just a free space propagation of quantum state, for example, via satellites. Or you can also use more sophisticated types of transmission protocols like quantum teleportation. And this is something that you will like to do if you want to communicate over very long distances. I mean, fibers will not work over very long distances because fibers are lossy and noisy. But if you want to go over very long distances, then you should probably resort to teleportation. So this is basically mean that between the nodes of your network, so this is just a network linked with the fibers or some quantum channels. So that means that these different nodes, they must pre-share some entangled states. And if they do this, then you can actually enable teleportation. That means faithful transmission of your quantum states in the entire network. This is not going to be the topic of my talk today. So I should mention that quantum communication can be used in different directions. So it's a mean of connecting quantum nodes, like shown here, where these different nodes could be quantum computers, and you want to connect these different quantum computers, and this can only be done by conveying quantum states. So this is quantum communication. You also use this in classical communication, actually, because if you want to reach capacity in classical communication, then the conclusion of that optimization, this maximization, is that you need to use quantum states of light, and you also need to use some sophisticated quantum measurement devices like coherent detectors, as we saw in one of the talks this morning. So for maximizing capacity, you also need quantum communication, and also for doing quantum cryptography, you need quantum communication, and this is what I will be talking about for the rest of my talk. So cryptography, what is this? So this is a way of hiding information. And this is, of course, of utmost importance in this information age that we live in. So we are doing financing, trading, or whatever, communicating with our bank. And this, of course, has to be done securely, and therefore we have to resort to cryptography. So the protocol that is used today is public key cryptography. And this is based on what is called one-way functions. These are functions that are very easy to compute, but they're very difficult to invert. For example, it's easy to factor, or it's easy to find the product of two numbers, but it's difficult to factorize a large number. This cannot be done by classical computers today because the classical algorithm for this is not known. However, this is not unconditionally secure, because I mean maybe one day we will come up with a classical algorithm that can solve this problem, or one day the quantum computer might be realized. A lot of effort, a lot of money put into quantum computing these years, and once we have a quantum computer, then it's no problem to invert this one-way function, and therefore it will render all crypto systems insecure from one day to the other. So we need to come up with a different scheme. You can use what is called the one-time path scheme, which is secure. So this is actually based on a pre-shared key. So the sender and the receiver sharing a key, and using this key, you can actually encrypt your message. You send it through a channel, and then it's decrypted at the receiving station. So this is a secure way of communicating. However, the challenge here is to generate or to establish this key. Of course, the two parties can meet on a bar and establish some keys, and then they can go to each of their companies or where they are, and then they will be able to communicate securely. However, this is not very convenient. We want to instantaneously generate the key, no matter where the two parties are placed in the world. And a way to do this is to use quantum tricks or quantum key distribution. This is a way to generate a unconditionally secure key or a secure key that can be used for unconditional secure communication. Okay, so we have the 3 parties in our network. We have Alice and Bob. So they want to establish the secret key, and they use a quantum channel, which could be, as mentioned previously, a fiber. And then we have also an attacker in the middle, an eavesdropper. And this eavesdropper, she's all powerful. So she has all kind of technologies, quantum computers and whatever. So this quantum key distribution was put forward many years ago, actually, back in the 80s, 84, by Bennett and Brassard. It's called BB84 protocol. And that was actually based on hard quantum technology. I mean, you need to produce single photons, and you need to use the single photon detectors in order to enable secure communication. It was then later realized that you don't need the single photon states. You can also do it with coherent states, which are also quantum states of light. But in these previous proposals, they also still suggested that you need single photon counters. But then about a decade ago, 10 years ago, we also realized that you don't need single photon counters. You can actually use off-the-shelf detectors, quadrature detectors. So just use off-the-shelf lasers, off-the-shelf detectors, standard fibers. You can actually do quantum key distribution. So that was a big breakthrough, and that also resulted in a lot of new startup companies over the last 10 years in this direction. So let me go through the protocol in greater details. So we still, again, have the 2 parties, Alice and Bob. They want to communicate via this quantum channel. So what Alice is doing is that she is encoding a set of random variables, x and p's, into a coherent state of light. And this is shown here in phase space, where x and p are the amplitude and phase quadratures. So you simply, in different coherent states, you encode these random variables. So these coherent states are then sent through this medium, the fiber, and then Bob is then performing a certain kind of measurement that can be a homodyne measurement, where he's measuring either the amplitude or the phase, switching between these 2 measurements, or he is trying to measure both quadratures simultaneously, so getting information about x and p simultaneously. So these are 2 different ways of measuring at Bob's side. That results in a set of random numbers, and these random numbers will then be correlated to the numbers that Alice was preparing. There will be some noise involved in this measurement and also in the preparation, because I mean we have place this noise disk on top of our state, because we know that coherent states are intrinsically quantum mechanically noisy. So there is some noise here represented by this disk that we cannot get rid of. And this is actually the thing that gives rise to security in the system. Okay, so this is the first step. This is the quantum communication step. But then there's a lot of classical post-processing. So, I mean, Alice and Bob, they have to communicate via classical channels afterwards. And they have to do, or Bob needs to do privacy amplification and error correction and stuff like this in order to map this, what is called a raw key, onto a secret key. And then having this, then they can communicate securely. But how do we know they can communicate securely? We have to compute the secret key rate. And this consists of 2 parameters. So there's the mutual information, the information between Alice and Bob that is generated by this set of data, minus the information that the eavesdropper is getting. So this is called the whole level information. So this is the maximal information that he can get given the numbers of the channels. So there's a certain number of amount of loss and a certain amount of noise in the channel. And given this amount of noise and loss, there's a maximum amount that the eavesdropper can get. This is the whole level information. And this, of course, this quantity k, the key rate, must be larger than 0, otherwise it's not secure. I should also mention that this is what we are doing. We are using a particular kind of state that is called a squeeze state. So it's not a coherent state where you have equally distributed noise for x and p, but you have squeeze state where it's squeezed in x, the amplitude quadrature is squeezed, but the phase quadrature is anti-squeezed. This is another way of encoding information. So if you compute the key rate, these are just theoretical simulations of the key rate as a function of the channel loss. So that could be a function of the distance in the fiber. So 10 dB of loss corresponds to, I don't know, 50 kilometers of fiber. And then you can easily compute the key rate. These are for different quantum states. This is if you use coherent state, and this is if you use squeeze state. So you don't gain much by using squeeze states. And squeeze states are much more difficult to produce in the laboratory. So in principle, just looking at this curve here, you just want to use standard coherent states. This is the key rate without any channel noise. There's loss, but there's no excess noise in the channel. Now, if you add a little bit of noise, is quite harmful to quantum key distribution. Then you're producing these plots again. You look at the key rate for coherent states. This is that one here. Then we cannot tolerate more than about 3 dB of losses, 50% loss, and then we cannot generate a secret key, secret communication. But if you now use squeeze state, then you can actually extend this distance quite dramatically. So here is actually you benefit from using squeeze state. So that was actually put forward in 2009, but here they actually assumed a large amount of squeezing, unrealistically large amount of squeezing. So you have a strong suppression of your noise. But we realized that you don't need that much suppression of the noise. You just have to combine it with some modulation technique. And that was our idea. So we produced squeeze state, just a reasonable amount of squeeze state, 3 dB of suppression of the noise, and then we combine it with a modulation channel here, just amplitude and phase modulator, which is combined with the squeeze state, which is produced here. It's a rather sophisticated apparatus. So you use 2 optical parametric oscillators, they interfere on a beam splitter. You perform a home line measurement, and then you project this one onto a squeeze state. And then you combine this with a modulation, and then you send it to Bob, and Bob performs home line measurements. So we carried out this experiment, and we demonstrated that you could actually transmit the state over longer distances than if you were using a coherent state of flight. So that was like a proof of principle experiment. It took off like half an optical table. So now we want to try to miniaturize the source for commercial deployment. So what we're using now is this centimeter-sized technology for our squeezers, for our optical parametric oscillators. So this is like 20 by 10 centimeters or so. So it gives some very nice squeeze state, but it's not. It's quite big. It's very bulky. We have also performed some other experiments, squeeze state experiment with millimeter technology. This is like a disc of lithium niobate, has a diameter of 0.5 millimeter or 1 millimeter. And now we're trying to use silicon nitride ring cavities. Exploiting the carrier effect for producing squeezed light. So we're trying to miniaturize the source. Okay, so there are some basic assumptions that we have put forward when calculating the secure key rate. So we assume that the eavesdropper, that she is almost all-powerful. So she has full access to the quantum channel. So she can attack the quantum channel as she likes. And there's no computational limitation. I mean, she has the most sophisticated quantum computer in the world. And she's also capable of monitoring the public channel, I mean, the classical communication between us and Bob later on. So this is what we assume. However, we also assume that she does not have any access to the stations of Alice and Bob. So she cannot interfere with the preparation station of Alice and the measurement station of Bob. So this is an assumption that is made in pretty much all security analysis so far. So we want to get around this, and then we are working together with Stefano Pirandola and Samuel Brownstein from York University. They came up with a different scheme on how to do quantum key distribution, where you allow for an attack of the measurement station. So here, the measurement station is not placed at Bob's station anymore. So we have Alice and Bob, and both Alice and Bob are preparing an ensemble or an alphabet of coherent states. So called alpha and beta. And these two ensembles of coherent states, alphabets, are then sent to a station in the middle called a relay. And here a measurement is performed where the two beams are interfering on a beam splitter, and then you perform a measurement of the amplitude quadrature and a phase quadrature. So you have two homodyne detectors here. And then you end up with some outputs which are just random numbers and doesn't make sense to the person who is measuring it. That could be Eve that is performing this measurement. So Eve has complete access to this station here in the middle. But there's just a lot of noise and does not make sense. And this will then be distributed, this noise or this set of data. And Alice, this set of data or the noise is somehow correlated to Alice's station, Alice's coherent states. So that by comparing these numbers from Alice, preparation station, and the numbers generated by the station in the middle, she can somehow predict what Bob has been preparing. And the same can Bob. Bob can predict what Alice has been preparing. But there's no measurement taking place at Alice and Bob's station. So this is called the measurement device independent QKD. So here we also relax the last assumption here. There's no access to Alice and Bob setups that we now allow for. And there's actually access to the measurement device in the middle by Eve. And this can be proven theoretically to be unconditionally secure. And we're now setting up this experiment in the laboratory. So my students are working on it in this very moment. Okay. Just if I have more time here in the end, I will just advertise a different quantum device that can be realized using the same type of technology. So this is a quantum random number generator. So random number generators are used in many places, and the technology that is often used is just the computer algorithm. The computer algorithm is producing random numbers, but it is not truly random because, the one who made the algorithm would know the numbers. And also, if the random numbers is produced by a classical source, some thermal state source, then in principle, these numbers that are generated, they might be random, but they're not unique. There could be someone else who has the same information about these numbers. They could be correlated to someone else. So what we want to do is to produce truly random and unique quantum numbers. And this can be done just by measuring the vacuum state of light, because the vacuum state of light, or just the vacuum state, is a truly quantum state. And by performing a measurement of a truly quantum state, then the outcome will be noisy. It will be truly noisy. It will be quantum noisy. So this is what we did here. So this is just the measurement of a vacuum state. And so the black line here is the electronic noise of the detector. And then we measure the vacuum state, and then we see a lot of noise. And this is truly random, this noise, if you believe in quantum mechanics. Then you cannot predict the outcome of the measurement of quantum measurement. The way to measure this is to use a homodyne detector, which is shown by this 3D graph here. So you simply have a beam splitter, you have a laser beam, you have two detectors, two intensity detectors, and then you take the difference of these two intensity detectors. So this is a homodyne measurement. Then what you're measuring is the vacuum port here. So the thing that is not entering. You're measuring nothing. And that is the vacuum state you're measuring. And then just by binning the outcome here, then you can generate a random string of numbers. So just by measuring nothing, you can produce truly random and truly unique random numbers. Okay, so I will come to the conclusion. So the main conclusion of this talk is that you can actually, by using squeeze state of light, then you can extend the distance for unconditionally secure communication. So the longest distance people have achieved so far in QKD with this technology, based on coherent states, is about 80 kilometers. But we will be able to extend this by a factor of 3 using squeeze states. Ongoing experiments. So we are trying to circumvent the assumption that Eve does not have any access to the stations of Alice and Bob by using a measurement-independent QKD system, and we're also trying to integrate our source on a chip to make it more commercially attractable. Okay, thank you very much for your attention.
Okay, let me allow for one question or two if we have in the audience. Okay, let's start here.
So go back to that last slide that you showed. So what is the black line?
So the black line here is the electronic noise. So that's the noise you see in your setup if you block the beam here. So this is just the electronic noise of your detectors.
So if the splitter is not exactly 50%, is there any bias in this or not?
No, there will be no bias. Of course, it should be as close as possible to 50-50, but it is not it's not that crucial. It is not creating any biasing. So it's the difference here that will give the noise. And if you have a small bias in the beam splitter, that can be compensated for in the amplifiers of the detectors.
But do you need to measure the output to determine if there is bias to adjust for that, or how do you know for sure there isn't bias in the data?
So what I mean, the difference here must be zero. I mean, the DC current must be zero. Otherwise, there will be a bias. That's the way we adjust it.